Sorry about the delay. I guess the keynote went a little over. My name is Brad Calder, and with me is Jay Herodis down here, and we're going to be going over Windows Azure Storage today. We'll start with a brief introduction on Azure Storage, then talk about some of the internals and how things work under the hood, then talk about what's coming, and then go over some best practices. So, what is Windows Azure Storage? Windows Azure Storage is a cloud storage provider providing anywhere at any time access to the data that you store into the Azure cloud. This consists of blobs, disks, tables, and queues. It's highly durable, available, scalable. And right now in production, we're storing over 8.5 trillion unique objects for our customers. And those customers are doing over 900,000 requests per second aggregate, so that's over 2 trillion requests per month. It's provided as a utility-based service, so you basically pay for what you use and store, and it's exposed with very easy-to-use and open REST interfaces, as well as the client libraries listed here. So let me first go through these data abstractions to give you a high-level view of that before diving into some of the details. So we provide blobs, and you can think of blobs as your file system in the cloud. It provides easy-to-use interfaces for storing files and retrieving those files. And customers are using this for data sharing, basically sharing documents, photos, videos, pictures, etc. They're also using it for big data analytics, where they're storing lots of data in the cloud, then doing compute over that data, doing MapReduce over that data to get some insights. Then there's the backups. A lot of customers are actually using the cloud for storing backups for their data, for on-premise, etc. So blobs are heavily used across these scenarios. Disk is a recently introduced concept for our VMs, where what we allow you to do is upload into our blob storage system VHDs. So you can use the existing blob interfaces to upload those VHDs, manipulate those VHDs in the cloud, and then you can take those VHDs and mount them with your VM. So your VM can use this network-attached durable disk. So the scenario we're trying to address here is that we want to enable customers to move their on-premise workloads to the cloud, and we want them to have a durable disk that they can use in the cloud. So any of the writes that you do to that disk basically go to our Azure storage system and we replicate it. So we keep that disk durable. Then another abstraction we provide is tables, and this is your, we'll do questions at the end, is tables, which provides a massively scalable NoSQL store. And what this allows is very efficient key value lookups. So customers are using this to store any type of metadata information for their service. So to store user information, device information, basically any type of metadata information you need to run your service. And then finally, for queues, we provide a reliable delivery of messages for your application. So customers are using this to perform asynchronous tasks, perform workflows, and basically to decouple the different roles of their application. So for example, you could have some worker roles that take some work from some web roles. And those web roles take the requests, they input them into the queue, and the worker roles asynchronously process them. And that allows the worker roles and web roles to scale independently. So these are the data abstractions we provide at a high level. Now, in order to use them, what you need to do is actually to create what we call a storage account. We provide storage in these 8 locations around the world. And what you would do is you actually would create your storage account in one of those regions. And of course, you can create storage accounts in any of the regions or multiple of the regions. But once you create your storage account, let's say in US West, then that means all your puts and gets are going to US West, where you created that storage account. Okay. So these are the 8 locations around the world we give you for creating those storage accounts and hosting your data. Now, once you create your storage account, you can then create blob containers and store blobs into those containers. You can create tables, put entities into those tables for your NoSQL store, as well as create queues and then store messages into those queues. And shown here is the REST protocols that you can use to basically access for your account your blobs, tables, and queues. Okay. So that gives you an introduction and a brief overview of the data abstractions. We're not going to go into the details of those here. This is an advanced talk, but if you want to know more details, there's lots of details about that online. What I'd like to do now is to give you some insight in terms of how we're using Azure Storage inside of Microsoft. Okay, Xbox uses Azure Storage heavily for several services. One such service is a cloud game saves. So if you ever play Xbox, it'll give you this option of do you want your, have your game saves in the cloud? If you choose that option, all of your progress and your game saves are actually stored into Azure Blobs. Halo 4 is an example where they store all of your key player statistics and information in Azure Tables. So for example, when you finish a multiplayer match, all your statistics are uploaded and stored into Azure Tables for you and your friends to view online. They use Azure Storage for Xbox Music and other Xbox Live components. Another system heavily using Azure Storage is Skype. Okay? If you use the video messaging service, all those video messages that you create are stored into Azure Blobs. Skype also keeps metadata in Azure Tables to allow Skype clients to connect with each other. So every single time you make a Skype call, a lookup is done to an Azure Tables to figure out how to connect to the destination device that you're trying to connect to. So every time you make a call with Skype, indirectly you're using Azure Storage. Bing makes use of Azure Storage for several ways. One way which is actually quite intensive is that we take the Firehose feeds from Twitter and Facebook and we ingest them quickly in near real time into Azure Storage. And then Bing indexes those in Azure Storage and then folds them back into the Bing search. Okay? The goal there is, as soon as you do a tweet or a Facebook post, to be able to actually search them in Bing within n seconds. And the last example I want to give is SkyDrive. So if you use SkyDrive, and anything you put into that SkyDrive folder is stored into Azure Blobs. Okay? So all your pictures, your documents, your videos, files, or whatever, that's stored into Azure Blobs. So I just want to give you some insight into how big of an investment that Microsoft is making into Azure Storage. And how big of a bet they've made on Azure Storage. As you can see, it's powering some of our most popular and highly scalable services. And then, of course, we actually have thousands of customers outside of Microsoft using Azure Storage, and shown here are just a few for an example. So now what I'd like to do is actually go into the internals of how we actually do some of the things in Azure Storage under the covers. When we set out to build Azure Storage, here are some of the design goals we had. We needed to have a storage system in the cloud that's highly available, and we needed to provide strong consistency within a given region. In talking to customers, it's pretty clear that they wanted to have strong consistency when accessing their data in that region, and they also wanted to have optimistic concurrency. Okay? The system has to obviously be durable, so we need to replicate the data. It needs to be scalable. Our system needs to actually scale over time to zettabytes of storage. We need to be able to have a global namespace to basically access your data from anywhere around the world. And we need to be able to automatically scale our storage system by just automatically monitoring what's going on to meet your peak traffic demands. Now, I'm going to go through at a high level some of these concepts around availability and consistency, but much more details are found in our SOSP paper. So let me start out by describing what a storage stamp is. So you can think of a storage stamp as a cluster or a tenant running in Windows Azure. This runs on the Windows Azure fabric, just like a compute service runs on the Windows Azure fabric. This cluster represents many racks of storage. It represents tens of petabytes of data. And when you create your storage account is allocated to one of these clusters, one of these stamps. And when your storage account is allocated to that stamp, all of your reads and writes to that storage account are going into this cluster of storage. Okay? Now, to create additional capacity, we actually stamp these new clusters out and allocate new accounts to them. So we just stamp these clusters out. And then we have what's called a location service, which manages the storage accounts across these stamps. It does things like account balancing, account allocation. It also sets up things like georeplication and handles georeplication across these stamps. Then in terms of replication, we have two types of replication in our system. Within a storage stamp, this is what we call keeping your data durable within a region. So we keep your data durable within a storage stamp at the DFS layer shown here on the slide. Then with a partition layer, we also georeplicate your data asynchronously if you're using geo-redundant storage. And I'll dive into both of these in a few more slides. Okay, so for this part of the talk, I'm really going to focus on what goes on inside of one of these storage stamps to keep your data durable, consistent, and available within a given region. So let's go through the three layers within one of these storage stamps. So the first layer, the lowest layer of our system, this is the system that's in charge of actually handling the disks. So this is the system that's responsible for persisting your data to those disks. And you can think of our underlying system as a DFS that's a JBOD system. Okay? So your data, when you actually store it into our system, is stored into the DFS system into these files which we call extents. Okay? And these extents are replicated 3 times within a region across different UD upgrade domains as well as fault domains. Now, one of the unique things about this underlying file system is that it's an append-only file system. So we never overwrite any data. We always keep on appending data to the end of these extents. So that's the lowest layer. The partition layer serves 2 unique purposes in our system. One is, this is the layer that actually understands our data abstractions. This is the layer that understands what a blob is, what a table entity is, what a message is, and how to perform transactions for those objects. Okay? And it also provides the optimistic concurrency when doing parallel transactions against those objects. The other thing that this layer is responsible for is our massively scalable index. Okay? This is the same index that's used to index all of your blobs, your table entities, and your queues. Okay? As you can see in the graph, there's this node with an M on it. This is a replicated master. And this master is in charge of taking this index and breaking it up into range partitions based upon the load to the index. So based upon the load to the index, it'll take this index, break it up into disjoint, contiguous ranges, and then assign those ranges out across our partition servers to load balance out the TPS traffic to that big index. Okay. Now, one of the key things here is, well, how do we provide this structured storage system on an append-only file system? We obviously allow you to update blobs in place. We allow you to update entities. How do we do that when the file system underneath is actually append-only? Well, the way we do this is what's called in the literature is a log-structured merge tree. I'm only going to go through this at a high level. There's more details about that in our SOSP paper. But it basically works like this. So we treat our data abstractions for the partition layer as these logs. Okay? We call these streams. So whenever you actually update any updates that come in for your data are actually appended to the end of these logs. What that means is that they're appended to the last extent in that log. So a log is basically a list link of these extents. All the prior extents in this list are sealed, and we never append to them. The last extent in this list we append to. So this is the log. And so the way a log-structured merge tree works is as follows. All updates get appended to the end of the log, and then your data is committed, and then success is returned back to the customer. Okay? In parallel, you actually have those recent updates also stored in memory. And we checkpoint those lazily in the background off the critical path of your writes. And those checkpoints are lazily merged into a B+ tree. That's where the merge tree part of the name comes. So there's really 2 parts to this system. There's the logs, which we use to quickly commit your updates. And then there's the checkpoints and the tree, which are used to find for reading what's the latest version of your data. So the checkpoints plus the tree is used to quickly find the last version of your data when we actually do reads. And the logs are used to quickly write your data and commit it as fast as we can. Okay, and that works very well for our distributed file system because our distributed file system is append-only. So these logs, we just come in, append them to the DFS, we're done, and we return success. And in the background, we do these checkpoints and the merge tree. Okay, finally, at the top layer, we have the front end part of our system, which provides a REST protocol for our blobs, tables, and queues. It does things like authentication, authorization, and this is sort of the inception point for gathering metrics and logging and other things like that. So if we have, for example, a write request that comes into our system, every write request has a partition key specified for it. And so what that partition key is indicating is, okay, I want to go into our massively index to a specific key point and then update that entity. So what we do is we cache in our front end a partition map, which is just a map of what partition server is serving what partition range. So we can quickly forward from the front end to the partition server that's serving the part of the index for the key we're trying to write to. So once we do that, we can then write the data into the DFS layer from the partition. And let me start by going into that just in a little bit of detail. So what I want to describe as high a level as I possibly can, it's a little bit detailed, is how do we provide consistency as well as availability for writing? This is a question we get once in a while. Well, as I mentioned, all writes to our system are just appends to this log. Okay? The data structure for a partition is this log. You're just appending to it. And you're always appending to the last extent. So to provide consistency and availability, the question comes down to, okay, how can we actually make sure that those appends to that last extent are consistent? So there's three things we do. All appends that are going on to that last extent, we make sure that the appends to all three replicas are in the same order. Okay? What does that mean? That means that each replica for this extent will be bitwise identical. And why is that important? Well, that means that we can actually read from any of the replicas. It doesn't matter. So we make sure that all three replicas are bitwise identical. We only return success to the customer if we actually done append to all three replicas. Okay? And then if there's a failure, or once this extent gets to a certain size, we seal the extent. And then we no longer append to it ever again. So let me go through an example of this. So let's assume we're doing a write, and we're appending our data to this orange extent. So there's three replicas for this orange extent. We're appending data to it at the end. And then let's say one of these nodes has an issue and goes away. So no longer can we actually commit this to all three replicas. So what we do in our system very quickly is we seal that extent. So we seal this orange extent, meaning that we'll never append to this extent again. And what we'll do is we actually have already allocated in the background other extents that are ready to go on three available nodes that we can start appending to. So we say, okay, let's take this new extent and just keep on appending for this log, for the partition layer. So we take this new extent that's shown in red, and we keep on appending to that, and we don't look back. And what we do is we add this new red extent to the end of this log for this partition, for the partition that we're working with. So our partition that we were working with had a bunch of extents, had the orange extent, which was being appended to. That's now sealed. Now at the end of that, it has this red extent, which we're now appending to for that log. And all new writes for that partition are coming in and being appended to that log. Okay. So to summarize here, the goal for writing here, since it's an append-only log system, is that we ensure that all extents are bitwise identical. If we have any issue writing, we just seal the extent, create a new one, and just keep on appending. And that's how we actually are able to provide availability even in the face of nodes being lost and certain types of network partitioning. Then lastly, if this node that has an X on it doesn't come back, the system will lazily take one of the healthy replicas for the orange extent and then copy it so that we always are maintaining three healthy replicas within the region. Okay, that's what we do for consistency for writing. Now, for reading, it's actually much easier to deal with this because all the hard work was done while we were writing. For reading, since all the replicas for an extent are bitwise identical, that means we can read from any three replicas. Okay? So for read availability, what we do is, let's say we have a read that comes in, and we're going to read from this red extent to serve up your read request for your blob, for example. If that node becomes unavailable while we're trying to do the read, what we do is we'll just issue another read to one of the other replicas in parallel. And we'll take the first request that comes back and then use that request to return the data to you. Okay? And there's some unique things we do here in that we dynamically are monitoring the latencies for different sizes of requests to the DFS layer. Okay? So, and if that latency goes above the 95% latency, we will automatically issue another request in parallel to one of the other replicas. So, for example, let's assume that the 95% latency for this request, size of request we're doing is 40 milliseconds. That means for 95% of the requests that we see, all of them are below 40 milliseconds. So if we go above 40 milliseconds for this request, that means something's going wrong. And we're not quite at the speed that we want to. So we'll just issue another request in parallel to one of the other extents, and then take whichever request that comes back to serve your request. Okay? Now, the next thing I want to go through to sort of wrap up this internals part is how do we do load balancing at the partition layer and the DFS layer? So for the partition layer, what we're really trying to do with load balancing here is to load balance out our TPS to that big index. So you're doing transactions against your table entities or your blobs, and we want to load balance that out across this index. So what we do is we have this master here. This master is continuously monitoring the load to the servers, partition servers, as well as to each partition. And let's assume that it finds, for example, one of the partitions is getting too hot. That means too many requests are being sent to this partition key range. Okay? The master will realize this within a few seconds. It'll say, okay, I need to load balance it. There's many different ways we can load balance it. They're talked about in the SOSP paper. One option is we can take this range partition, and we can actually split it into two smaller range partitions. So let's assume we do that in this example. So we split this into two smaller range partitions, which represent the full bigger one. And then let's offload part of that index to a different server that's more lightly loaded. Once that's done, we update the partition map so that we know where to send the request for that part of the partition range. The front end can then forward those requests to that new partition server, and then that balances out the TPS load. Okay? So one of the very important things here is that when doing this TPS load balancing, we actually don't move any data around. As you can see, we haven't moved any data around in the DFS layer. All we're doing is taking part of the partition range index and saying, okay, server X, stop serving that part of the index. Server Y, start serving that part of the index. That's all we're doing. Okay, now for the DFS layer, there's sort of three things we do for load balancing. One is we actually monitor the load for the storage nodes as well as the replicas, and then we use that to guide which extent replica we're going to use to read from. In addition, we issue these retries in parallel under the covers whenever the request is taking larger than the 95% latency. And that's what we do for reading. For writing, we do a similar thing. We monitor the load of the nodes and the replicas that we're actually appending to the replica set. If we find that something's being overloaded, we'll actually seal the replica and then start appending to a new extent and put that at the end of the log, using the same exact technique we just talked about for write failure. Then finally, one of the unique things we do here is load balance capacity. So what this does is it actually moves the replicas around in our system to ensure that all the nodes in our system, and potentially even the disk, have some free space to use. Okay, so why is that important? Well, our DFS layer is an append-only system. That means we would never write anything in place, never update anything in place. So if you actually had a certain percentage of storage nodes that were completely full, you could only write to these nodes that actually had free disk space, since we never write in place. Okay? So you have to make sure that at least there's some free space on all your storage nodes to help alleviate, as best as possible, hotspots, and to actually use as much IOs and spindles across your systems that you possibly can for writing. You know, one important scenario there is if we lose a disk or a node or a rack, we want to re-replicate that data, those extents, replicas that were lost, as fast as possible across all storage nodes that are available, that are remaining available. And by having space available on those nodes as well as all their disks, that allows us to best to do that as quick as possible. Okay, So hopefully that gives you some insights in terms of how we actually do things under the covers. Just the takeaways, just to summarize this, is for durability, within a given region, we keep at least 3 replicas. For consistency, we keep the replicas bitwise identical and only commit the data once we actually write the data across all 3 replicas for an extent. For availability, you can read from any 3 replicas. If there's any write issues in terms of write latency or failures, we just seal the extent, add a new extent at the end of the log, and just keep on writing. Don't look back. And for performance, we basically have this retry on 95% latencies, and we do the auto-scaling and load balancing for the partition layer and the DFS layers I just described. And there's much more details in the SOSP paper if you're interested. Okay. Now, let me talk about what's coming. So the things that we're working on for this calendar year are a georeplication, a new service called Windows Azure Import Export, real-time metrics, cores, JSON, and some new features for the .NET 2.1 library. And so we'll go through these now. Now, before we talk about georeplication, I just want to re-summarize that when you actually have a storage account, there's actually 2 types of durability you can opt in for. One is what we call local redundant storage. That means your data is kept redundant within a single region. And there's geo-redundant storage, which means that your data is kept durable in 2 regions. 3 copies in the primary region and 3 copies in the secondary region. Okay. So for geo-redundant storage, the motivation here is to provide additional durability in the face of potential major regional disasters that potentially could occur. So we keep your data durable 400 miles apart from each other. And what we're pleased to announce here at Build is that we're now geo-replicating all queues for geo-redundant storage. So for your geo-redundant storage accounts, we're basically geo-replicating all of your data, your blobs, tables, and queues now. Now, when you use geo-redundant storage, you choose the primary region in which to host your storage account, and every primary region has a paired secondary region in which your data is geo-replicated to. It's shown here. So we've actually paired up all of our regions. So we paired up US West and East, US North and South, the 2 in Europe, and the 2 in Asia. So what that means is, for example, is if you create your storage account in US West, then that means US East is your secondary location. Same thing, if you created your storage account in US East, then US West is your secondary location. So we've paired up each of these regions. And when you actually write your data is written into the primary region, and your reads go there right now. And then we asynchronously, off the critical path, replicate your data to the secondary region. Okay, so let's go over how sort of this works right now. So let's assume we actually created your storage account in the US West region. When you do that, we create a DNS entry, as shown here, for your account for both blobs, tables, and queues, pointing to the US West storage stamp in which your data is located in. So all your reads and write requests go to US West. Then in the background, we asynchronously and lazily replicate your data to US East. Now, right now, if there was actually a major regional disaster, we would actually perform a failover by contacting the customers and then updating this DNS entry to point to US East and for this storage account example. So once that's updated, then your request would be redirected to US East, and your existing URLs that you currently use would work. Now, there's a few things to go through here. One is that this failover will only be triggered by Microsoft if we can't recover the data in the primary region. Okay? And one of the reasons for that is that the geo-replication is asynchronous. So that means that if we did a failover, then the recent updates that had not actually made it over to the secondary region could potentially be lost. That's why we only want to use this as a heavy hammer if we cannot recover the data in the primary region. Now, we typically geo-replicate the data within a few minutes, though at this time there's no SLA for actually how long it will take to do the geo-replication. Now, where do we want to go with this? Well, where we're headed is that we want to actually give customers control over this failover. So we want to actually expose an API for the customers to basically say, fail me over now. switch my primary from US West to US East. We want to give that control. On the way to that, there's two features that we've been working on for this calendar year. One is make sure we have all queues geo-replicated, and that's done now for build. And then the other thing we're looking at deliver by the end of this calendar year is read-only access to the secondary location. And that's what I'll be talking about now. After we ship that, then we'll be looking at providing the customer-controlled failover in the future. So what scenarios can you actually use the read-only access for? So with this scenario, you're going to get read-only access to the secondary location, so you'll be able to do your gets. You won't be able to do puts or deletes, but you'll get access to an eventually consistent copy of your data in this other region. So if there's any unavailability for the primary, you'll be able to actually get access to your data, though it is an eventually consistent copy. Now, this also provides a second source for reading your data in both locations. So if you had your primary to be US West, your secondary to be US East, now you have your data in both, so if you actually had compute or customers in both regions, you now have faster access to that data. In addition, if you did compute in the secondary region, egress is free within that same region, so the egress would be free within that region. Now, for your applications to use this concept, they have to be able to use eventually consistent reads. Okay. Now, how will this work? Well, when you provide this feature by the end of this calendar year, you'll be able to go into the portal and enable basically read-only access for your storage account. Once you've enabled read-only access, you'll now have two endpoints in which to access your data. Shown here is the primary endpoint. This is the URL that you get today for accessing your storage account for blobs, tables, and queues. Then in addition, you'll get this new endpoint that you can use to access your data for reads, which is the same account name dash secondary. Using this URL, you'll be able to do a get to basically get an eventually consistent copy of your data in that other region. Note the same storage keys you use for the primary will work on the secondary. So when accessing your data, it sort of goes as follows. All your writes still go to the primary, and your reads to the primary are strongly consistent, and your reads to the secondary are eventually consistent. Okay. So you can use those two endpoints to access your data. The other thing that we're going to provide is for the client library, you'll be able to actually specify some options to help guide which region to go to. So for the client library, we'll provide these options like primary only, send my read request only to the primary, secondary only, send my client library read request to the secondary only, and options like primary then secondary. So what that option would do is, under the covers, we have retry logic in the client library. What that would say, if you get a failure when doing a access to the primary, for the retry, try the secondary. So we're trying to make that easy to use this from a client library's perspective. The other thing you'll be able to do is actually query the max georeplication delay for your storage account. So you'll be able to query for that storage account separately for blobs, tables, and queues. What is the georeplication delay for that? So let's say the delay was 5 minutes. That means that the data in the secondary for your blobs is 5 minutes behind the primary. The updates are. Okay? So you'll be able to query that once we release this feature for your storage account. And finally, you'll have actually separate statistics for accessing your, to see how much reads are going to the primary, as well as how much reads are going to the secondary for the storage metrics. Okay. So the last thing I want to go over before turning it over to Jay is a service we are going to be providing called Windows Azure Import Export. This allows you to move terabytes of data into and out of Windows Azure blobs by shipping disks. And so there's two scenarios that we support, both import and export. Let me just quickly go through those. Okay. So for import, as a customer, you'll be able to download some tools to basically prep your disk for import. For this service, all disks must be BitLockered. Once you've put the data on those BitLocker disks that you actually want to import to your storage account, you'll create a job. You can do this via REST or through the portal. And that import job, you'll specify the BitLocker keys, the storage account information, and other things like that. And then we'll return to you a mailing address. Now, with that mailing address, you'll then ship the disks to us. We'll receive the disks. The operations folks will plug them into our service. We'll read the BitLocker key from our service to transfer the data into Azure Blobs, and then remove the disk and ship them back to you. And during this whole process, as a customer, you'll be able to monitor the progress of your job via the portal as well as REST interfaces if you want to. Okay? Export's a similar process, just a few minor differences. One is you'll actually specify to us with our tools what blobs do you want to export. We'll use that to determine how many disks are required. Then you'll go create a job via our portal or REST interface, and we'll specify how many disks that you should ship us, and we'll tell you where to ship them. You'll then ship those empty disks to us. We'll then plug them into our service, put the blobs into those disks. The disks are now going to be BitLockered. So once we ship the disk back to you, you would then download the BitLocker keys to get access to the data securely on that disk. Okay? So at a high level, that's how import and export works. And just to summarize the features, you'll be able to access the submitting of jobs and the progress of these jobs via our portal as well as REST interfaces. And for each job that you want to actually import data into an account for, each job can only import data into a single account. So if you want to import data into multiple accounts, you would actually submit multiple jobs. Same for export. And each job can be up to 10 disks. And the disks we support for the first version of this are 3.5-inch SATA drives. As I mentioned, all disks must be BitLockered. Okay? Now, Jay's going to take over and start talking about real-time metrics and then move on to best practices.
Good morning, everyone. And yeah, like Brad said, we have a slew of features to talk about. I'll start off with real-time metrics. About 2 years back, we had released this feature called Analytics, which provided you metrics at an hourly granularity and logging. These two together provide you a lot of valuable information where you can actually learn about how your service is performing when it's talking to storage and make a lot of improvements using these. We're glad to announce that this year we will have real-time metrics, which is per-minute aggregates of your metric information for blobs, tables, and queues, and this data can be up to 5 minutes of delay. And you can enable real-time metrics very similar to how you're enabling your current metrics, which is through set service properties. And this data will be stored in your namespace. A common question that we get asked is, would turning on analytics impact your live service? No, it does not. The reason is because when we write this analytics data into your namespace, we write it into a different namespace per se, though it's stored in your own storage account. So it does not impact your live service as such. In addition, it provides a lot of valuable information, so we highly recommend turning this on. So obviously, real-time metrics, this is per minute aggregates. So you can use this to monitor your application a lot more closely and in real time itself. And a thing that it provides, which hourly aggregates do not provide, is a closer look into your performance, right? Because an hourly aggregate can smoothen the spikes that you may have in your traffic. And just to make a point, the next two slides kind of compare these two. So here I have an hourly metrics for a live service which is running. It does about 680K requests, a little under that, per hour, which boils down to about 188 requests per second, right? Nothing wrong out here, smooth kind of TPS out here throughout the 24-hour period. But when I take an hour and get into its real-time metrics, that's when I see spikes. The reason is this service is every few minutes, it's spiking up to about 300 requests per second. And spike load is not the best when you deal with scale scenarios as such. You have to aim to kind of smoothen the load so that our load balancing can react to it, right? And so real-time metrics kind of gives you this insight into your data or how you are accessing the storage service. And this is the real-time settings. It's very similar to the hourly aggregates that we provide, where you can enable it. You can include your APIs, because it's at both levels, right? At the service level and at the API level. And so you can include API details, and we'll see this in running in one of our test tenants as such. Retention policy, you can turn on retention policy, and this gets garbage collected for you. So you don't have to go and delete it. The other thing that we're announcing is cores. Yes, it rhymes with doors. And so we will be releasing cores this year. And what it provides, what is cores as such? So by default, a browser would not allow a JavaScript that your web app has to access storage directly, because it's cross-domain. So the browser is not going to allow this unless the storage service now provides you with certain headers that follows the cores standard as such, or the mechanism that the browser has included to kind of bypass this security or prevention per se. And so you can set your cores on your storage account so that now blobs, tables, and queues will provide these cores headers so that your web app can directly talk to the storage service rather than running a proxy service. You can control the origins that this needs to be accessed from. You can control the request headers and the response headers, and also a lot of other settings like caching and things like that. So you can control a lot of things pertaining to cores using, again, set service properties on blobs, tables, and queues. This is an example of a core setting which allows get and put methods to be invoked on your storage service. This particular setting has allowed all origins. You can have specific origins in there. And it allows all request headers and all expose headers. And so you can control this based on what you want to do with your application as such. And max agent seconds is basically 180 out here, which tells the browser, do not send an options request to me for 180 seconds. So you can cache the previous options response for 180 seconds as such. This information is used by the browser. The other thing we are pleased to announce this year would be JSON. It is a popular, concise format for REST protocols. And OData supports two protocols, AtomPub, which we currently support. But the problem with AtomPub is it's pretty beefy. It has a lot of CRUD in there, which you really don't need when you're writing a table service per se. But that's the OData protocol which is there. So they've included a new protocol for JSON. And in JSON, there are multiple flavors. And one flavor particularly interesting is the no metadata. This assumes that the client is smart enough to understand the data that comes across in their Azure table, and so can kind of interpret the data as such without requiring any metadata from the Azure service, table service. Why is this important? The reduction in bandwidth usage is almost close to 70, or sometimes actually it's exceeded 70%. And a lot depends on how your entity is structured. But in most of our runs, the savings is more than 70%, and we will see an example of that. And moreover, many applications also use JSON as their object model. And this is an easy transition from your object model to a wire protocol. And so you don't have to kind of convert into XML or serialize this XML per se. So there's a lot of savings in there for your own application, and reduces costs for your own application. And there's a lot of goodness around JSON. So we're pleased to announce that this year we will have JSON. We will also be releasing an RC build of 2.1 very soon, sometime next week. And what this provides is async task. So you can do async await, which a lot of folks have asked us. And so we've finally introduced that into the 2.1 library. And it supports cancellation. So overall Uber cancellation for your method, you can provide a deadline for it per se and control that cancellation. In addition, a lot of you missed the byte array text and file upload methods in the pre-2.0 library. And so we understand that you missed it a lot, so we brought it back now in the 2.1 library with a lot of optimizations underneath. The thing that we introduced in 2.0 library is a table service layer. This layer was built with one sole purpose of supporting a NoSQL store. Unlike the WCF library that the .NET produces, which is meant for either a relational store or a NoSQL store like Azure Table, we built a component called table service layer from scratch for NoSQL store. And so it has a lot of optimizations in there, and our performance is almost 40% to 50% better based on how your access patterns are. And so we had that in 2.0. What was missing in the table service layer is the ability to use link queries against it. And we've introduced now an iQueryable provider for the table service layer, so you can get back to writing your link queries as such. In addition, we've provided compiled expressions. And what is compiled expressions? Basically, today, when you have an entity, when you're using a 2.0 library, it uses reflection if you don't control serialization. And what compile expression brings to table is a lot of optimizations around it, so that it compiles this, it dynamically compiles an expression to optimize your serialization of that entities across the wire. And so we have that in there. In addition, we've done a lot of performance improvements. We've introduced buffer pooling. There's a multi-buffer memory stream, because .NET memory streams have certain overheads when you use async methods on it. And so we've introduced a multi-buffer memory stream for that purpose. In addition, what we've also done is the .NET MD5 calculation is turned on by default rather than using the native one, just because it's more performant. And this library should be available via NuGet sometime next week. So let's go to a demo on the new features. So this is a web app I have out here, which uses JavaScript internally. And what I have here is it's going to use this JavaScript directly. It's going to enable cores on my account. And it's going to use JavaScript to upload blob without going through a proxy service. This is a lot of bandwidth that I can save, because I don't need a proxy service, don't need to pay for a compute that needs to scale as much as Azure Storage. So it directly talks to Azure Storage as such from my browser. And just tends to be a better experience for users too. So I can go and kind of browse. Let's say I take this one. And if you look at this, what it's done is it issued an options request. And let me just go magnify it. So as you see here, the blue one is what I had run previously, just in case the demo gods disconnect me from internet. But here I have out here an options request that was sent to upload this particular blob. And if you look at it, it sent an options request. It sends the origin name, which the browser sent it, because the process is the browser. The browser sent an options request on my behalf when I had this AJAX call to the storage service. And the Azure service responded by saying, yes, I allow this origin, and you can allow get and put methods with all the headers that I need to provide. So it provided all this information back to the browser. The browser says, OK, this is safe to call now, and allowed this put request to go through and upload this blob to the cloud. Similarly, it did a get method out here to kind of display this blob. I can go, and this magnifier is kind of going to stop it for now. Right. And if I go kind of refresh this, it's going to get all the images, listing of all the images, and I can go and scroll through all the images that I have here. And so this is kind of the course demo as such, where we are running, we enable cores on our storage account, and that enables the browser application to directly talk to storage. Oops. Definitely don't want this. The other demo I have here is for the real-time metrics itself. As I said, I've enabled real-time metrics. Out here, I'm showing all the APIs that I've called, and if you look at the the information that is provided, it's provided for basically all the uploads that I did and downloads. But here it is aggregated at the service layer. If I enable a list option, this is where I get the information saying, OK, this is my pre-flight request that the options request that the browser sent. I had about, let's see, about one request that I just performed while uploading the blob. And then, of course, I uploaded an image, and that shows up in my real-time metrics. So this is almost instantaneous that I got the metrics back again to figure out, OK, what happened to my request, or what is the average latency that I'm facing, and things like that. So all the columns in real-time metrics is still the same compared to your hourly metrics. You have availability. You have the average latency. The only thing that has changed out here is your minute keeps changing, and it's more real-time. So whenever you use the storage service, you'll have an entry out here for that particular minute, where we start showing the data for you. The other thing that I wanted to show while accessing this real-time metrics is I actually used JSON for it. And back to the magnifier. So if you look at this, what this asks for is JSON and no metadata. And what I got here is just the JSON payload. It's just the raw payload that I've got without any metadata. The metadata information that could have been retrieved is what is the data type for certain more complex data types than ints and strings, or rather more than strings and ints. And I think there's also date time, so it can tell you what data type the particular field belongs to. Out here, I've asked for no metadata, and so if I had asked for minimal metadata, it would have returned me that information as to what the type of a value is out here with the metadata, with the JSON data. Just to compare AtomPub with JSON, what I'm going to do here is I'm going to reload this and remove this, because by default, in this particular version, we're still going to have AtomPub. If you look at the payload, it's nearly 6 times. There's more than 70% of savings out there. So it's about 1.4K for JSON, and it's about 6.7K for AtomPub for the same set of data that I've retrieved. So there's a huge savings in bandwidth when you start using JSON. It's extremely useful, especially when you start having a smarter client that understands the payload, and it doesn't require sufficient metadata as such. So you could do all the metadata interpretation on your client side. And so JSON would save a lot of bandwidth. It'll save a lot of cogs and give you better performance. At the end of the talk, if I have more time, I might go through more of these new features as such, especially the real-time metrics as to how you can use it. But for now, I'll just get back to the slides, because I think we have a sufficient set of best practices to cover. So with respect to best practices, a general best practice for .NET itself is disable naggle. Naggling along with delayed act can cause a lot of latency. The reason is, especially when your packet size is less than 14K, the TCP naggling and delayed act can add value, or rather add latency to your round trip as such. And so you can disable naggling on the service point manager. Disable expect 100 continue, and I have an asterisk out there because most of the time you would want to disable, except if you're very sure, or rather, except when you're not sure whether your request is going to succeed. What expect 100 continue is, when you're trying to upload some data, what it sends is an expect 100 packet, and the service is going to respond saying, yes, you can send the rest of it back, rest of the payload. And then the client would send the rest of the payload. So if you're trying to upload a large blob as such, and you're not sure if it's going to be successful or not, then you can have expect 100, and it's going to be beneficial. But otherwise, you can disable expect 100 and save on this one extra round trip that would occur. You can one of the recommendations is to always increase the number of default connections. .NET by default has 2, and this has hit a lot of our users as such, where they're not aware that the default setting is 2, and when they try to run their application, they don't get enough throughput as such, just because there's just 2 connections to the cloud. And so you can also kind of interpret this from your analytics logs where you only see 2 requests reach us, and your analytics logs is going to say, okay, 2 requests came at this particular time, and then after the response was sent back, you see 2 more requests in your logs as such. So you can interpret this and investigate this by yourself if you hit this particular problem where you're running out of connection limits. The other thing I would really call out here is take advantage of .NET 4.5. It especially has this new background server GC as such, which is pretty awesome. And so use this. The GC, even the other GCs the performance has increased quite drastically. So I would recommend switching to 4.5. Some general best practices as such: locate your storage accounts close to compute or your users as such. This gives you faster latency because of the RTT. In addition, if your compute is co-located with your storage, obviously you don't pay for your egress. So there are benefits out there which most of you might already know. In addition, understand the storage account targets as such. One of the things that you can do if you want to achieve more than what a single account can give is create multiple storage accounts to get more out of the storage service, and also distribute your storage accounts across geo-regions based on where your users are. Cache critical data sets. That's one of the higher points where if you want better latency than what is provided, or if you want consistent latency than what is provided, the best thing to do is caching. Almost all the services that Brad pointed to have some sort of caching in there to go and fall back on. So this is quite important if you want to have a service that scales, but also need some latency guarantees as such. And it allows you to get more requests per second, too, than what a single storage account can give or multiple storage accounts can give. The other thing to remember is to distribute the load across various partitions. Rather than creating a hotspot on a single partition, tend to select your partition keys. And we've given you that control because the blob name is a partition and you control the blob name. The queue name is a partition and you control the queue names. And in addition, the partition key in the table entity gives you the control on the partition that we have. Right? So distribute the load across these different partitions and avoid spikes for better scale. Use HTTPS because it provides better security as such. This is, again, kind of a no-brainer, but that's, again, it's good to remind yourself to use HTTPS, especially when you're using SAS, which is shared access signatures. It's highly recommended. Optimize what you send and receive. And this is, again, a general best practice when you develop an application, right, a distributed application. You want to reduce as many round trips as possible. And so for blobs, you have something called range reads, where if you're downloading the blob, and if it fails, you can use a range read to download the rest of your content that you failed to download in the first place. Of course, we have blob metadata and head requests that can kind of give you all the metadata that you want. You don't have to download the blob just to get the metadata. Tables, we have a upsert which we introduced sometime last year, and what this allows you to do is reduce the number of round trips. In a lot of scenarios, you want to insert an entity if it does not exist, or update if it exists. And if you're not sure whether it exists or not, it's best to do an upsert, so it's going to do the right thing behind the scenes. Projection is another thing where you can select just the properties that you need rather than getting your entire entity, especially useful when your entities are large. Point queries are the best. They perform the best. It's a key value store, so all the point queries where you're directly targeting a single entity would perform the best. Queues, you have update messages and batch where you can start storing states, and also batch sizes to control your gets. You can control parallelism at your application layer. You need some kind of throttling so that if you're a multi-tenant system, you don't kind of overwhelm other users just because a single rogue user is using your lot. So it's good to kind of prevent a lot of unbounded access to the storage service layer. You need to keep a tab on it at least. Enable logging and metrics. I think I've kind of called this out multiple times. This is very useful for you. You can provide a retention policy where storage service would go and delete your old data. So you can, for example, have the hourly metrics for a longer time, but real-time metrics for a shorter period of time to enable you to go and investigate your application or learn from your application access. Blob best practice, try to match your read size with your write size. This is something which is very useful, especially streaming, where if you stored 1 MB blocks as such, your block blob where you stored 1 MB blocks, but then you're reading only, let's say, 2K of chunk for your streaming scenario, this is pretty expensive in terms of I/O. So it's best to kind of match your read size and your write size, and you have control of that while uploading in the client library. The two questions that we get asked pretty frequently is, how do I upload a single blob the fastest, or how do I upload a lot of blobs in my container the fastest? And so to kind of explain these two, the next two slides would do justice to it, but I want to introduce two terms. Concurrency. Concurrency is multiple workers, how many workers you have, and these multiple workers kind of uploading different blobs. Remember, one blob is a partition, right? Each blob name is a unique partition. From parallelism perspective, it is multiple workers working on different blocks within the same blob. So it's uploading these different blocks in parallel for a single blob and then committing it at the end. So you have these two knobs with you, concurrency and parallelism. And so let's compare this. We ran it on an Excel VM where we uploaded 512 256 MB blobs. So this is a total of about 128 gigs of data that we uploaded using an Excel VM. And this is the graph we had. C1P1, which is just a single connection trying to upload the entire blob. There's no parallelism, there's no concurrency out there. It gives you about 13.2 megabytes per second. If I upload different blocks within the same blob, which is C1, and 30 workers uploading different blocks, it averaged me about 51 megabytes per second. And if I upload multiple blobs with a single parallelism factor as such, no parallel upload of blocks within those multiple blobs, then I achieved about 96 megabytes per second. Why is this? With C1P1, what happens is you have a single TCP connection to the storage service. You're bound by the TCP rate control and round trip time. And so this is going to kind of restrict your latency as such. So you're talking more about latency, and you have a single endpoint. The difference between the parallelism of 30 versus concurrency of 30 is that concurrency of 30 would always give you better throughput because it's targeting multiple partitions. Remember, we are built for scaling out based on your partition access, right? So our system can split and serve these two ranges separately. So accessing these multiple partitions will give you better throughput as such. And so the test completed almost twice as fast, and single blob, as I said, is bound by a single partition server, and that's why I just got about 51 megabytes per second, whereas multiple blobs kind of saturated the NIC on my Excel VM. Same thing with download. If I try to download just a single blob, I got about 96 megabytes per second, and we get faster download here because our service does some prefetching as such, which enables this faster download. With respect to concurrency of 30, obviously it gave me a lot more, where I saturated the NIC on my Excel VM. I got about 130 megabytes per second. With respect to table best practices, a common question that we get asked is, how do I best design my schema in a NoSQL store? We have a lot of books for relational store as such, and it's a good art out there which has been well documented for relational store. For a NoSQL store, a few things to remember out here is that your schema should be driven by your scenarios as such. So you need to ask what your critical queries are, and select your partition key and row key to avoid these hotspots. A good example is if you're, let's say you are the social media company that is allowing all the users to come in, and all the content belongs to a particular user, your user ID can be a partition key. And it's fine if you have 1 million users. We use range-based partitioning system, and it's not going to impact your system just because you have 1 million users. So it's basically fine to have every entity belong to a new partition with a different unique partition key as such. And so a NoSQL design is kind of driven by your scenarios, as I said. So you need to figure out what your critical queries are. In addition, we have batch transactions. And batch transactions is providing you atomic transactions where all the entities belong to the same partition key. So that constraint kind of can be used to design so that anywhere you need an atomic transaction across entities, you can try to fit them using the same partition key as such, so you can use the batch transaction. It's a schemaless store, so you can store multiple kinds of data types in the same table as such, under the same partition key. So you can have your customers and orders in a single table with the same partition key if you need transaction across that customer and order. We provide you a single index, which is partition key row key. If you need more, you can always concatenate columns to form this composite key as such. With respect to entity locality, the way you need to start thinking is all your entities are sorted by your partition key, row key. This combination is your clustered index. So what you could do is, for your applications, determine all the entities that need to be accessed together and try to keep them in a sorted fashion in the same table as such. So again, getting back to the customer order scenario, your customer and order can have the same partition key and then differing row keys as such, and they're clustered together if you want to retrieve all the orders for your customer. So this kind of reduces the number, all the clustered entities, it reduces the number of IOs that the service has to issue to kind of return your entities back again. In addition, the table service client layer in 2.1, like I said, the table service layer has a lot of optimizations, was built from ground up for NoSQL, so tend to use that, and we've added iQueryable provider so you don't lose the link functionality while using the table service layer. With respect to queue best practices, one of the things that you need to note out in a queue service is getting the message is not necessarily deleting that message. So it's a two-phase of operation. And the reason why we've done this is for durability, because your worker role could retrieve a message, and before it processes it, it can crash. In which case, if we had actually deleted the message, that message would never have been processed. So instead, what we provide is when you get a message, you can provide an invisibility time, and this message now will be invisible for any other worker which is trying to dequeue. Once your worker processes the message, it can go and issue a delete on it. And so making this message processing idempotent, because if your worker fails to delete this message on time, this message is going to be visible again to your different worker as such. And so you have to make this processing idempotent, and there are a lot of ways to do this. One simple way is having a message, unique identifier in your message to say that your action has been done. In certain cases, by default, that scenario is idempotent, and so it is fine for you to just go ahead and process it. But in a lot of cases, like if it's credit card transaction or something of that sort, you have to keep a unique ID to make sure that you're not processing it twice. You can also benefit from update message. So what update message gives you is the ability to change the content of the message, and also ability to change the invisibility time that you set on your message. And so you can use update messages to store state, especially for a long-running worker which is processing the message. You can start storing this intermittent state to reduce wasteful work. Message count, we provided you a message count for these for your queues, and you can use this to basically go and scale your workers as such. So if you want more number of workers, whenever your message count increases, you can do that using your service management APIs to scale your workers as such. DQ count, you can use it to identify either poison messages. So every time you DQ a message, we increase a count. If you see this count increase and the message is still valid, it means that either it's a poison message where your worker is refusing to process it, or it could also be that your invisibility time that you're setting is very low. So it could be either one of these, and using your logs, you can actually go and figure out if it's one of these scenarios as such. Blobs to store large messages, and this is one more pattern that a lot of people have used to kind of increase their batching concept. So what they do is store multiple messages, and a message size can be 64K. So if it exceeds that, what they do is store this message offline in a blob and store the blob index into the message. Now, when they process the message, they would retrieve that blob, and they'll get a higher throughput as such, because now you can go and process more messages with a single request to the blob store. And so this kind of pattern can give you a larger throughput when you want using Windows Azure queues. You can also use multiple queues as such. This is a scale-out scenario where you use more number of queues to process more. And so you can, a queue is a single partition, and what happens while creating these multiple queues is now you're targeting multiple partitions as such. With respect to resources, we have our Azure website itself, and the developer platform out there has a lot of examples for .NET, Java, Python, so you can always download that and give us your feedback based on what you see out there, what you like, what is missing, and things like that. We would really appreciate your feedback. In addition, Windows Azure Storage blog. This is the best place to figure out if there are new services coming along, and also learning more about our internals as such. So we keep blogging a lot of interesting things out there. The SOSP paper is always a good guide to learning more about our internals. And of course, we would love to know more about what you thought about this session, what you would like to hear, and things like that. So please do send us your evaluation. That's about it.